Welcome to Mechanical Drawing and Design N6. Today's presentation is going to be on belt drives. This is a module that you saw already before, so some of the things will be very familiar to you, but we will also introduce some stuff that you haven't seen before. So pay attention. I will try and explain as easily and as simply as I possibly can, making it possible for anybody to actually understand. This is not a difficult module, but there is a bit of understanding that you need to have. Let's begin. So first we will speak about the types of belts that you have. So the first type is the flat belt. And this is a picture of a flat belt that you see on the screen. The reason it is referred to as a flat belt is because when you look at it, it's pretty much flat. Okay, and so if we cut a section of that belt, this is what you will have. And if you look at the cross section of a flat belt, okay, what I have highlighted with a blue strip here, you can see that the cross section is a rectangle. This is a zoomed view of this cross section of the flat belt. You can see that the cross section of a flat belt is a rectangle, and the dimensions of it will be like this. Okay, W is the width and T is the thickness. Okay, and as you can see again, for a flat belt, the cross section is a rectangle, and therefore the location of the centroid will be right in the center of that rectangle. Now, the position of the centroid of the cross section of a flat belt and any belt that we're going to deal with is very important. Okay, this is one of the geometrical features of the cross section of a belt that you need to know, because it helps you to get another very important geometrical feature, which is called the effective diameter. Okay, so we're gonna get into that, but suffice to say at this moment that it is important for you to also know where the location of the centroid of the cross section of the belt is. Okay, so for a flat belt, which will have a width W and a thickness T, the location of the centroid, of course, will be in the center of that rectangle, because we know that the centroid of a rectangle is, of course, at the center of the rectangle. And so the distance there is what we refer to as Y bar. And as you can see, Y bar is going to be equal to the thickness divided by 2. Okay, so that is pretty much the height from the bottom of the belt to the location of the centroid. That height is equal to the thickness divided by 2. We call it Y bar because that is the Y coordinate of the centroid. Okay, very important. Now, let us assume that we have this flat belt wrapped around a pulley. And of course, as you will know by now, whenever you have a pulley system, there is always one pulley that is larger than the other. So for the sake of this example here, we will assume that this pulley is the large pulley, okay? And for those of you who've never seen a pulley before, this is what it looks like in 3D. And you can see that you do have some space there where the belt can actually wrap itself around the pulley. Okay, you can see the space that is created there. Okay, so this is one example of a pulley that is designed for a flat belt. Okay, it's a 3D example just to give you an idea of what it looks like in real life. But when we are drawing for simplification purposes, we will just draw a circle. And you can see here that wrapped around the pulley, you have the belt, okay? And now what is really important for us is to look at some of the geometrical features that we have here. So the first one I am going to speak about is the radius of the pulley. And so this is the distance pretty much from the center of the pulley to the outer surface of the pulley, okay? So this is what we refer to as the radius of the pulley, okay? So it does not measure into the belt, okay? So we measure this radius on the pulley only, okay? So that is the radius of the pulley. You need to see how it is measured. And then besides that, you also have what is of most importance to us, the effective radius of this pulley, okay? Now, when you have a belt wrapped around the pulley, the effective radius will be the distance that goes from the center of the pulley to the centroid of the belt, okay? I will repeat that. The effective radius goes from the center of the pulley to the centroid of the belt. It's very important to remember that, okay? And so, as you can see, the effective radius is different from the radius of the pulley. The radius of the pulley does not take any measurement into the belt. It's only the radius of the pulley. However, the effective radius of the pulley will go from the center of the pulley all the way to the centroid of the belt, okay? And that is what we will refer to as RE to say effective radius, and RP here was the radius of the pulley, okay? And so we can see therefore that the effective radius is equal to the radius of the pulley plus y bar, okay? Because y bar is the distance from the bottom of the belt to the centroid, okay? So if we measure the effective radius, then that is equal to the radius of the pulley plus y bar. And when you're dealing with a rectangular cross section for the flat belt, y bar is equal to the thickness of 2, okay? So you can pretty much say that the effective radius is equal to the radius of the pulley plus the thickness divided by 2, or if you want, you can say half the thickness, okay? And so now that we have the effective radius, we can easily find the effective diameter. And it is the effective diameter that is going to be most useful to us, because all the equations that we use in this module are written in terms of the diameter and not in terms of the radius, okay? So it is the effective diameters that are going to be useful to us. And so we need to find the effective diameter. Knowing the effective radius, of course, the effective diameter is going to be equal to twice the effective radius. And so if you multiply RP by 2, that will give you twice the radius of the pulley, or just the diameter of the pulley. If you multiply half the thickness by 2, what you will get is the actual thickness, okay? So therefore, the effective diameter is just equal to the diameter of the pulley plus the thickness of the belt, okay? Now, this is the case when you are dealing with a flat belt, because y bar is equal to T over 2. So if you multiply that by 2, it gives you T, okay? And why do we multiply everything by 2? Is because the effective diameter is equal to twice the effective radius. Now, when we deal with the large pulley, we will use capital D to refer to its diameter and capital R to refer to its radius, okay? But if it was the small pulley, we would have used small d, okay? And so just bear that in mind from now on. When you're dealing with the large pulley, you use capital letters for its dimensions, and when you're dealing with the small pulley, you use small letters, okay, small d, for its dimensions. Okay, so this is how we find the effective radius of the large pulley. Capital DE will be equal to capital DP plus T. For the small pulley, the effective radius is small de, it's going to be equal to small dp. Small dp is the diameter of the small pulley plus the thickness. Okay, so these are important equations to find the effective diameter. The second type of belt we're going to deal with is the V belt. Okay, very, very important. Okay, the V belt. And now the V belt will look like that. Okay, this is what it looks like, and you can see why it is referred to as a V belt. It's of course because it's got a cross section in shape of a V. Okay, I hope you can see that the cross section here is like a V, but in real life usually you may have more than one V belt. Okay, so you can have a series of V belts together and it will look something like that. Okay, they have been joined together to make one big belt. And so when you look carefully here, you will see that it's almost as if you had 4 V belts that have been joined together to make just one big belt. Okay, so it's not always that you will have one belt like this. You can have a combination of them. that are joined together on one pulley. And so the cross section, of course, as you can see here shaded in blue, has the shape of a V, okay? Very important. And since that is the cross section of the belt, you can expect the pulley to also have a shape in such a way that the groove here where the belt will come and sit is also in the shape of a V. Hence, it is called the V groove, okay? When you're dealing with a V belt, the groove inside of the pulley here, it's called the V groove, okay? This is very, very important. It's called the V groove, and sometimes they can also give you the V groove angle, okay? Very important. And if you are dealing with a belt that has many V belts joined together, kind of like what you have here, okay, then of course the pulley will look something like this. You can see here it's designed for two V belts, okay? So you can have a situation where your belt is actually two V belts joined together, and so the pulley will look something like this because it's got two V grooves to actually house the two V belts. Okay, so you can see how the belt is going to fit here in the V groove, okay? I've put its cross section there to show you how the belt actually fits inside of the V groove, okay? This is very important. And so in real life applications, the V groove angle here is somewhat smaller than the included angle of the belt, okay? And so if we look at the cross section of the V belt, of course, you have this shape, and this is a trapezium. Its dimensions look like that. So that is what we will refer to as the width of the V belt. And this will be the thickness of the V belt, but it is also referred to as the depth. Okay, so if you come across the expression depth, just know that it is not different from thickness. Okay, so if you see that you are given the depth of your V belt, just know that this is no different from the thickness, okay? Very, very important. And so if we extend the lines from this side of the trapezium and from that side of the trapezium, like this, okay, the angle that we will get here is what we refer to as the included angle of the V belt, okay? And it is usually going to be 40 degrees, okay? So the included angle of your V belt is usually 40 degrees, okay? So if it is not given to you in your exam, they didn't write it in the question, you can just assume it to be 40 degrees, okay? But usually they will give it to you. So the included angle of the V belt, okay, is that angle here that you get when you extend the lines from these sides of the trapezium, okay? The angle you get there is 40 degrees, and that is the included angle of a V belt. It is usually 40 degrees. So it will be given in the question, but if not, you can just assume that it is 40 degrees, okay? And so you mustn't mix up the included angle of the V belt and the V groove angle. They are not the same. Now, the V groove angle is the angle of the V groove on the pulley, okay? The angle of that opening, okay? That is what we refer to as the V groove angle, the angle of the V groove on the pulley. That is the V groove angle. The included angle of the belt, that is the angle that you get here, which is generally 40 degrees. So do not mix the two, they are not the same, okay? Although in some cases you may have to assume that the V groove angle is also 40 degrees because the belt included angle is 40 degrees. Okay, in some cases you may have to assume that, but do not think that they are always the same. You could get a question where the included